Hey everybody, I'm assuming it's live. You're gonna have to tell me that it's live. Somebody has to confirm my existence. I'll wait. There we go. All right. Thanks, Kim. Okay. Hey everyone, welcome to the 25th anniversary question show. This is the March 23rd, so we are 2 days after. On Saturday, March 23rd was is that right? Sunday? Saturday was the 25th year that I have been running Universe Today. I founded the website on March 23rd, 1999. And although I don't have any of the articles still on the website, you can use the Wayback Machine to find an old version of the site. An awful, terrible version of the site. And it's a totally different world now than what it was when I started. But yeah, 25 years of doing this job. And now, who knows how much longer I'll still be able to do this job until the robots come to take away space news reporting and replace it with, Neil deGrasse Tyson crying, saying, we discovered aliens beyond the universe with the James Webb Space Telescope. Those AI videos they're just everywhere. I think I asked this. I think I asked you all last time or a couple of times ago. Is YouTube unable or unwilling to deal with all of this AI spam? I mean, I know they just put in some new regulations where if you're using AI to misrepresent things, then you have to disclaim it. But if you just spool out goo, science gobbledygook, does that count? I don't think so. I think right now that's fine. And this is going to be a toxic poison that will corrupt YouTube from within, destroying it. All right. So let's get into this. So hey, welcome to my weekly question show. Your questions, my answers, blah blah blah. Now this show lasts for 2 hours, and although you might have thought it's mandatory, it's actually optional. You can leave anytime you want, so don't worry. So the first hour is more structured, and this is where we are recording the QA that comes out on Tuesdays. A week later, comes out 8 days later, which gives Chad time to edit it. And then at the 1 hour mark, so at 6 o'clock my time, we will switch and we will do overtime, where we will just hammer out as many questions and answers as I have energy for, and then we will end. So if you've never done this before, go ahead and put any questions that you have into the YouTube comments, and the moderators, Zapfan and John Seffel, will take those questions and they'll put them into a database where I will be able to have them right in front of me, organized. I can read them quickly and answer with no just fluff in between. Now, I give emphasis to the people who have never had a question answered before. I can see how many times we've answered your question in the show. So if this is the first time you've ever asked a question, then I like your chances. I am just a journalist. I'm not a scientist. And so if you're going to ask me to provide an opinion on someone else's scientific opinion, I cannot do that. I can give you opinions on journalism-related matters. I can give you opinions on running websites and Vancouver Island flora and fauna. Bears are cool. Sea otters are weird. But I cannot give you any additional scientific information. What do I think of the cyclical universe? I have no opinion. And then finally, I try to run a simulation in my mind of sort of what is the recent stuff we've tackled in the question show. And so if I feel like we're just going to retread the same, Fraser, do you believe in aliens? That kind of thing. So, okay. Let's get into the question show. Berries are tasty. Yeah, the thimbleberry is the finest berry on planet Earth. Change my mind. You've probably never even had one. Okay. What do I do now? Yeah, okay. And there you go. We are live. Yes, I am recording. Here you go, Chad. Those are the colors. Okay. Robert W. Cote. How do we account for gravitational lensing of the cosmic microwave background radiation? Do we really have an accurate model of where all the matter, both light and dark flavors in the entire observable universe is enough that we can reliably unlens the CMB? When astronomers first discovered the cosmic microwave background radiation, and over the years as different spacecraft like COBE and WMAP were launched, they were able to map the cosmic microwave background better and better over time. And one of the things that they knew was that there was a little bit of fuzziness in the cosmic microwave background. And this was coming from the combined gravitational lensing of all of the photons that were traveling from 300,000 years after the Big Bang to us today. And that these photons had to go through all of these galaxy clusters and past galaxies. And it's kind of amazing when you think, like, each one of these photons survived the entire journey. They traveled for 13.8 billion years and they never hit anything. They never hit a star. They never hit a planet. They just went from leaving the cosmic microwave background, I guess, leaving a point in space, traveling for 13.8 billion years, and then arriving at our detectors. But one of the hopes when the Planck satellite was developed by the European Space Agency, that when it would launch, one of the things that it would do is that it would be so accurate that it would be able to measure the amount of gravitational lensing, the combined gravitational lensing that went on with these photons. And then the hope was that then they could de-lens the CMB, that they could sharpen it by knowing essentially on average how much photons were shifted away from their positions. You could then go back and look at the original CMB measurements, and then you could change them to adapt for the gravitational lensing. And so they were able to do that. And with enormous accuracy, they were able to get like 9 sigma accuracy in the measurements. And so in addition to measuring the cosmic microwave background with more sensitivity than had ever been done, it was able to do this de-lensing of the CMB. It was also able to measure the lensing of it was also able to measure the lensing of the polarization of the CMB. And so, you know, when you wear polarized lenses and you're sitting in a 3D movie and then you like take two of the lenses and you put them beside each other and they block the light out, or you turn the light and you can see different parts of the movie, right? That's the polarization of the light that's coming from that movie. It's done on purpose to give one eye one vision and the other eye a different view of the same movie. And so they were able to actually measure the effect of the gravitational lensing on the polarization in the CMB. So it's like safe to say that the Planck mission was one of the most successful science missions, and this de-lensing was just one of its to-dos that they were able to check off when they wrapped up the mission in 2018. Whitney Adams 4008. Can you please explain the difference between a nova and a supernova? I've heard there's potentially an upcoming nova event and I want to know more. No problem. Yeah, so I want to talk about the event first, and then I will sort of wrap that up in the difference between a nova and a supernova. So the event is that there is a star called T Coronae Borealis that has been known to flare as a nova every 80 years or so. And astronomers have measured its brightening several times in history, and the last time was in 1946. And Corona Borealis is a tiny little constellation that is smack dab in between Hercules and Bootes. So it's very familiar in the Northern Hemisphere. If you know where Hercules is, it's to the right beside Hercules, in between Bootes. Bootes looks like a kite. Hercules looks like a dude. And it's right in between those two. And one of the stars in that constellation is going to brighten. But I need you to prepare yourself for what this is that you're about to see. This star is practically invisible to the unaided eye. It's magnitude 10. You need a pair of binoculars or a small telescope to be able to see it. And over the course of this nova event, it's going to brighten to magnitude 2 at the most. And just to give you a comparison, the North Star, Polaris, is magnitude 2. Not the brightest star in the sky, but it's fine. You could see it. And so unless you know exactly where you're looking, you won't even know that there is a new star in the sky. It'll be around for a couple of months and then it will fade away. So I think a lot of people are quite excited. So imagine, right? You go outside and there are thousands of stars that you can see with your eyes. And there's a new one that's roughly the same brightness as many other stars. And then it's gone again. So, it's scientifically, it's incredibly fascinating, and it's going to be really cool if you know what you're looking for. And so, go out now, learn where Hercules is, learn where Bootes is, and then learn where Corona Borealis is, smack dab in the middle. Learn those constellations. Both are really fascinating. There's a lot of really interesting things in both of those constellations, and that part of the sky to the northern hemisphere is quite easy to find. A lot of really interesting things there. So that's the preparation that I recommend. So what is it? What is a nova and what is a recurring nova? So a nova occurs when a white dwarf star has siphoned off material from a companion star. So you can imagine there's a white dwarf star in orbit around another star, and they're close enough that there is this tidal tail of material that's going off of the star and down onto the white dwarf, and it's wrapping around the outside of the white dwarf, building up into this layer of material on the outside of the white dwarf. And at a certain point, so much material is on the outside of the white dwarf, it's heated by the gravitational pull that is squishing it down, that it undergoes this thermonuclear explosion, explodes off the surface of the star. The star is very bright for a short period of time, and then it fades again, and the process starts again as more material starts to accrete onto the outside of the star. That is a nova. And nova happen on a regular basis. Astronomers know of many of these recurring nova, and then other times they find these nova for the first time. So that's a nova. Nova is a white dwarf star that experiences a temporary outburst because it has stolen material from a partner. A supernova is when a star explodes. And there are a variety of causes that can get you to a supernova. So one line of them is that you have a star that's much more massive than our sun. It's fusing material in its core. It is no longer able to fuse in its core, and the outward pressure of the light stops, and all of the outer layers collapse in on itself, and it explodes. And that's called a core collapse supernova. And that's like the simplified version. But there's another kind of supernova known as a type 1a supernova. And these are explosions of white dwarf stars that have reached 1.4 times the mass of the sun. So when a white dwarf, like the one that our sun will eventually turn into after it finishes the main sequence phase, it will become this object that is less than 1.4 times the mass of the sun. Like obviously, right? Like the mass is 1 times the mass of the sun. And so it will be less. It is essentially the exposed core of the sun. But if, again, the sun was next to some partner star and it was siphoning material, building it up on its outer surface, it would be creating these layers. They would blast as nova, but some would be left over, and they would pull in more material and blast as a nova. And slowly over time, it would accrete enough material that it would reach this thing called the Chandrasekhar limit, which is 1.4 times the mass of the sun. And when that happens, then you don't just get this flash off the surface of the star, you get an explosion. The star disintegrates entirely and creates this incredibly bright flash. And astronomers use these type 1a supernovae as a way to measure distance in the universe, because that number, that 1.4 times the mass of the sun, you know intrinsically how bright the explosion is that you get to see in the sky. And then when you measure the brightness that you can see, then that tells you the distance. And if that happens to go off inside a galaxy, then you know how far away that galaxy is. And because they're so bright, these are very useful way out to billions and billions of light years away for being able to measure distance in the universe. So, oh, that's probably done. Okay. Dreamcast Night. Could the Hubble constant be corrupted by the galaxy's movement towards the Great Attractor, and has anyone been looking for such evidence? That's such a great question, and that's a very clever insight that you've had. So the question is, like, we know that there is this discrepancy in the measurement of the speed of the expansion of the universe, that for the methods like using Cepheid variables or even the type 1a supernova, you get one measurement. And then when you measure the expansion rate of the universe based on the cosmic microwave background, you get a different measurement. And that was thanks to the Planck satellite that I mentioned in the first question. Wow, the whole thing is coming together. Anyway, and this is called the Hubble tension, the crisis in cosmology. And so the question that you're asking is, like, we know that the Milky Way is part of this large supercluster of galaxies, and we can see that galaxies are sliding towards some center of gravity that is on the far side of the Milky Way. And the question you're asking is, well, like, could that motion of the Milky Way as it's getting pulled towards the Great Attractor, like all these other galaxies, could that account for some of the error in the Hubble tension? And the answer is yes. And in fact, astronomers have looked for this. So we know that the Milky Way is part of the local group. The local group is part of the Virgo supercluster. The Virgo supercluster is part of the Laniakea supercluster. It's sort of like the largest structure. It's 500 plus million light years across. It contains about 100,000 galaxies, and it is influencing the Milky Way's movements through the universe. And so astronomers recently did a study where they calculated how much effect would this motion of the Milky Way's movement through the Laniakea supercluster impact our measurements of the Hubble tension. And the answer they got was not zero, about 2 to 3% of a modification on those measurements. But here's the problem. It's in the wrong direction. So in other words, that if you account for the Milky Way's movement towards the Great Attractor, you would actually get a even greater difference between the measurement in the Cepheid variables and the measurement in the cosmic microwave background. So yes, the effect is there, and no, it doesn't solve the problem. If anything, it makes it worse. Oh, this is awesome. Paul Lathrop. I live at 43 north latitude, and all my life I've seen shadows on the moon go from side to side. And this past week, when I was visiting at 18 north latitude, the shadows seemed to be going bottom to top. What gives? Now, I don't know exactly sort of where you are and what you were seeing, but I have a similar situation. I live at 49 north latitude, and I have been to places like Costa Rica, which is closer to the equator. I'm not exactly sure where it was. And I've also been to Australia. And yeah, when we are like, I'm sort of imagining standing out on my deck and I'm looking at the moon and I'm seeing the direction that the crescent moon makes and which side of it is a shadow. And yet, when I was in Costa Rica, closer to the equator, the whole moon felt like it was rotated and it was more like the bowls of a horn. Bowls of a horn. when I was at the when I was close to the equator and I was looking at the moon, the whole thing looked like it was rotated. It was more like the horns of a bull. And yet, when I was in Australia and I looked at the moon, it was completely reversed. And so if it's this way, and I don't know whether it's going to be reversed or whatever, but if it's this way when I'm at home, it's this way when I'm at the equator, and it's this way when I'm in Australia. It's about where I am on planet Earth. So when I'm standing close-ish to the North Pole of the Earth, I'm looking at the moon from one perspective. But when I'm at the equator, I'm effectively on my side and I'm looking at the moon. And then when I'm in Australia, I am upside down looking at the moon. And so that change that you're seeing in the direction that the shadows of the moon are happening is entirely based on your position on planet Earth. And you just experienced like one of the obvious implications of being on a spherical Earth when you look at the moon. Very cool. Pelican 666. Any thoughts of putting the deep space network in space? Maybe only need one location. There are no plans to build the deep space network in space today, but it would be an amazing improvement to the current capability of our spacecraft. So right now, there are a large number of giant radio dishes down here on Earth, and these are the Deep Space Network. And these are what NASA uses to communicate with the different spacecraft that are all around the solar system. And in fact, you can actually go to the Deep Space Network website, and then you can see all of the different radio dishes, and you can see which ones it is communicating with at which time. So you can see that this 70-meter dish in California is talking to Curiosity, and that 70-meter dish in Australia is talking to Perseverance, and so on. And the position of the dishes is that they can provide coverage of the entire solar system as the Earth is rotating. The problem is that it is oversubscribed and that we are just launching more and more spacecraft. And not just what NASA is launching. You've got the European Space Agency, you've got Japan, you've got all these different agencies, and they are all attempting to communicate with their spacecraft. And the bandwidth is running low because a spacecraft that is looking, because a radio dish that is looking at one spacecraft cannot then receive any data from any of the others. And so they all have to queue up and wait for time on these big dishes as they track the different spacecraft. Send and receive all the data, move on to the next target, send and receive all the data. And so just like in general, more dishes are needed to keep up with the increase in capacity requirement from all of these additional spacecraft. But the big problem is that the farther away a spacecraft is, the more signal attenuation that you get, the slower the bandwidth that you can receive from that spacecraft. Like with New Horizons out at Pluto and beyond, it's only able to send in a couple of bytes a second when it's attempting to transmit at a much higher bandwidth. It's just that the signal is very weak by the time it reaches Earth. You've got to have a gigantic radio dish to be able to receive the transmission. So there are a couple of solutions to this. One is to switch the way transmissions are done. And recently with the Psyche probe, NASA tested out using laser communication to send messages to and from to Earth from the spacecraft. And they were able to send just an astonishing amount of data. And they built a hybrid version of one of their big dishes where it's got this traditional radio dish and then it's got a laser like a telescope built into the middle of it. It's able to receive laser signals as well. And they were able to find that they were able to get about 40 times as much bandwidth with this hybrid approach. And so you can imagine, okay, all future spacecraft are going to have these laser transmitters in addition to their radio transmitters. And that's going to allow them to send and receive communications at dramatically higher bandwidths. That should decrease the load across the deep space network. But the other thing you could do is you could put these spacecraft out across the solar system so that they can receive the signal and then transmit with a much larger transmitter. And then that means that you don't have to put as much hardware on the spacecraft themselves, just enough transmitter to reach the relay point and then move and then be able to send that data back home. The Chinese Space Agency just launched one of their relay communications satellites called Chichao-2. And this is the second one. The first one helped with an earlier mission at the moon. And this is going to be at the far side of the moon. Well, it's actually, this spacecraft is in orbit around the moon, but it's able to see both the far side of the moon and Earth at all times from its orbit. And so as the Chang'e 6 mission goes to the moon, does a sample return mission in the next couple of years, from the far side of the moon, this relay satellite is going to be able to receive the signal, send it to Earth, and to be able to receive commands and send them down to the spacecraft. And so you're going to probably see this increased infrastructure over time of relay spacecraft. You could have some big transmitter just sitting at Mars that is then collecting all of the information from all of the rovers, bundling it up into one big package, sending it to Earth with a big transmitter. That would be a huge savings in sort of radio telescope time here on Earth. So more infrastructure is always needed. P. Guzman, will there be a test? No. Keep it chill here. Reland Fellner, should NASA consider assembling an Aldrin cycler between Earth and Mars before sending humans, kind of like the Lunar Gateway? So the Aldrin cycler, this is a spacecraft that is proposed by Buzz Aldrin and has been proposed in other scientific concepts as well. And this is a spacecraft that would travel from Earth to Mars and back and forth, kind of like a regular ferry service. And a good example of something that's like that is, I don't know if you remember in The Martian, there was this spacecraft that was carrying all of the astronauts to and from Mars. And then they switched to their own descent vehicle. And this spacecraft was making a sort of return trajectory from Mars. And so the idea is that you've got this spacecraft that is making this regular just trip, orbital, from Earth to Mars, back and forth. It requires minor changes to its orbits to be able to make the meeting points of both Earth and Mars. And so as it gets close to Earth, then the astronauts launch in their rocket and then they rendezvous with the cycler, they get on board, and then they fly on it. And it's got like better facilities, lots of food, lots of power, lots of comforts on it as they make the long trip, better radiation shielding as they make the trip to Mars. And then when they get to Mars, they hop off and maybe they go to Phobos, or maybe they actually do an entry onto Mars. And then another crew launches off of Mars, docks, rendezvous with the cycler, and then follows it back to Earth. And then they return to Earth. And there's a lot of really good reasons. Like, this provides redundancy and safety for the astronauts during that multi-month, it could be 6-month, could be 9-month trip from Earth to Mars and back again. And to be able to have a safe place where people can be, where you know it's done, it's launched, all of the materials on it, has everything that the humans need. All they have to do is get on their Dragon capsule, like they launched to the International Space Station, and just meet with the cycler. So that's a great idea. Now, a lot of people think that it's not necessary, that it's kind of redundant. And so, you know, I'm sure if you ask someone like Elon Musk, he'd say, well, just launch on Starship. Everyone gets on Starship, they take all their gear, they fly to Mars, they land, and you don't need this complicated, intense ferry system to take people to and from Mars. And we'll see how it all plays out, but I think the idea is pretty cool. I'll talk about the three-body problem in overtime if you want. I have seen them. So LLM is asking, there's the observable universe, the accessible universe, and the complete universe. I've never heard of that before. What is that? I don't even know what that means. complete? Incomplete? So LLM, if you can provide me some clarification. Dop3 dog, is there a limit on how many elements can fit on the periodic table? I think the question you're really asking is there a limit on how many protons that you can pack together into a single atom? And like theoretically, no, there's no limit, but practically there absolutely is a limit. And there are certain atoms that are stable, and you don't have to get very far up the periodic table of elements to start reaching unstable atoms. Like even uranium, plutonium, these things are unstable and they fall apart, decay after a certain amount of time. But in giant particle colliders here on Earth, scientists have been able to build atoms, and I don't know what the current number is. It's in the 120s, I think, for the number of protons that are on it. But these things are incredibly unstable. They fall apart within a fraction of a second, and they're not seen naturally in nature. And so a question that people ask is, like, could we expect there to be some island of stability where we might, with bigger and bigger particle accelerators, get to a place where we're able to build atoms that have 200 protons and they're stable and they're unobtainium and you can use them for some cool effect? And the answer is probably not. And that's because the universe is the greatest particle collider we can possibly comprehend. Think about a kilonova where you have two neutron stars. So each one is the result of a black hole. Each one is the result of a supernova. They are the remnants left over. They are the size of a city, and yet they have several times the mass of the sun. They're incredibly dense and compact. And you take two of these things and you smash them into each other. Just like think of the masses involved. When astronomers saw the kilonova explosion several years ago, the first one, they saw many Earth's worth of gold produced instantaneously in this colossal explosion. And you have got to assume that even more massive particles were formed in this kilonova explosion. And yet they all would have just decayed away almost instantaneously. What's left are the stable elements that we see in the periodic table. Like the periodic table isn't a rule of nature. It is a handy way for us to perceive the elements as we find them in the universe when we think about how their masses, their behavior, how their electron shells work. And so the universe, when it explodes stars and crashes neutron stars together, can come up with vastly more complicated particles than we can comprehend, and yet we don't see them. So if the universe could make them and they were stable, then we would see them, and we don't. So we can just safely assume that we will never make them either. Buzzkill, Fraser. I want my island of stability. So we're going to have adamantium and unobtainium. Correct order. I again bring up the vote to use Earth as a Star Trek planet in channel video. Does anybody second the motion? Chad, can you add Earth to the list of Star Trek planet names while you're editing this? Good call. Should just be Terra. John Pettit, it's been over years since the link between supermassive black holes and dark energy was proposed. Debunking, checking, and interest has been going on since. What's your take on it? Is it dead? I did an interview with the researcher behind it. It's not dead, but nobody has confirmed it. So, a lot of theories live in this world where someone proposes something, the math seems to work, other people don't get around to checking it, no one confirms it, just lives in this twilight zone in between. John R. Wachowski, are you sure you're pronouncing Betelgeuse correct? I'm told it was pronounced Beetlejuice. It doesn't matter. I mean, people call it Betelgeuse. There are so many different pronunciations for this that it just doesn't really matter. And I think, for a lot of people, the movie Beetlejuice kind of ruined it. So you're like, oh, if I say Beetlejuice, and if I say it one more time, you know how this plays out. Cosmic collisions. How interested in science and astronomy were you as a teenager? What was your high school experience in physics? I was super into space my whole life. As a child, I had a book of Our Universe, which was like a Time Life series of books that you could receive and pay in installment payments. And they had something else on Searching for Underwater Treasure and a couple of other books, but the Our Universe one was the one that I loved. I had the original version before the updated content for the flybys of Uranus and Neptune by the Voyagers. And then when I was in high school, I got into astronomy again. In fact, there was a garage sale and somebody was selling all of their sky and telescope magazines. They had just piles and piles of them. And so I got them for cheap, and I just went through them, magazine after magazine, reading about space, looking at the pictures and looking at the ads for telescopes. And then when I was 14 or so, I bought my first telescope. I went to Vancouver. There was a telescope manufacturing company in Vancouver, and I bought, it was a 4-inch Newtonian reflector on, or it's like a 4.5 inch, 4 inch on an alt azimuth mount. So it's like up, down, side to side, didn't track the sky at all. And I was out every night with this telescope, and I learned my constellations, and I observed all the planets, and I saw, galaxies and star clusters and things like that. And then I would set it up when my parents had parties, and I even organized star parties on this island that I grew up with in Canada. And then when I was in high school, I studied journalism in my high school, like my high school newspaper. And I reported on things you could see in the night sky every month. So I talked about how you could find the Big Dipper, or I was really intense. And so my physics and math and all that was fine. I went into engineering at University of British Columbia. So I had, I took calculus in high school. I took physics 12. I took chemistry, algebra 12, all of the prerequisites. And then I went to engineering and really didn't enjoy it. And so switched and went into computer science, and like my career was working for a web development agency out of Vancouver, and also started a software company and various things like that. And so I sort of forgot about space in my early mid 20s. And it wasn't until I was 28, 27, I was reading The Case for Mars by Bob Zubrin and Pale Blue Dot by Carl Sagan, and was just getting into space again. And there weren't a lot of great resources back then. You read books. This was sort of before the World Wide Web was really starting. But then I watched the landing of the Mars Pathfinder mission with the little tiny rover that it deployed. And we could watch this live. I was at work and we were watching all of the updated information that was coming from this mission. Wait, was it Sojourner? Yeah, Sojourner was the little rover. And then I was like, you know what? I want to start a website about space and astronomy just because I want to learn more about this and I want to cover a bunch of this stuff. And that was in 1999. So 25 years ago when I started Universe Today. So I've always been into space and astronomy. I kind of forgot that I loved it so much for my early 20s and then found it again and then turned it into a career. Daniel Roach, what is the best thing to see from a southern latitude? So there are four things that are extremely cool to see from the southern hemisphere. So those of us in the north, we can't see these at all. It's only when you get closer to the equator that you can actually see them. So I would say the first thing is the Magellanic Clouds. These are kind of like mini versions of the Milky Way. They look like puffs of cloud in the sky. And when you go outside, if you know where to look, you can see the Milky Way. If you go outside and you know where to look, you can see the Milky Way and it's sort of stretching across the sky. And then you see these two clouds that are close to the Milky Way, but are very distinct. They look good in dark skies. So that's the first thing. The second thing that sort of blew my mind is the largest globular cluster that we can see is visible, Omega Centaurus, the Omega cluster. And it is the biggest. And I got to see it I was at a star party in Australia and I got a chance to see it for the first time. And it's amazing, just like a colossal globular cluster. And they're probably one of my favorite sky objects. The next thing is that you can actually see Alpha Centauri. You know, we always talk about Alpha Centauri. It's the closest star to the sun. And yet, for most people who live in the northern hemisphere, you can't see it. And so it's sort of weird to think about this hypothetical star that we just never see. And yet you go down to the southern hemisphere and someone asks someone who knows the sky, point out Alpha Centauri. Oh, it's right over there. That's Alpha Centauri. That's that closest star that we've heard so many stories about. And I'd say the last thing, and maybe this is about being closer to the equator, but when I was in Australia, the Milky Way goes directly overhead. From my perspective, the Milky Way is down at the horizon. It just rises above the mountains. I can see some of the constellations in the Milky Way, but then it comes back down. And so to see the heart of the Milky Way, the very core of our galaxy, directly overhead, which is like the best viewing, is just mind-blowing. And in fact, when I was in Australia, also Saturn and Jupiter, a bunch of planets were also in that same area, directly overhead. And that is not an experience that I am accustomed to have to crane back to look straight up to see planets. They are always down close to the horizon because of my position on the globe. So I highly recommend, if you've never seen the sky from the southern hemisphere, you should definitely do it. And of course, that weird moon is upside down. That's so bizarre. Fraser's at least 25 years old. Yeah. Nomad77CA. Why were stars in the early universe so much larger than the stars today? From what we can tell, stars today are limited by the amount of mass that they can accrete. And it's about 100 times the mass of the sun. Maybe it's a little more, maybe 150, maybe it's a little less. But what happens is, as this giant cloud of gas and dust is collapsing down into the star gets hotter and hotter at the core, and then it starts to blast out winds, stellar winds. And over time, the stellar winds balance out the infalling material. It heats up the entire rest of the nebula in its environment so that it no longer wants to collapse down until the star, as it forms, puts on the brakes of its own development. And so we just don't see stars that are more massive than this. They all are preventing, they're limiting their growth. But it's believed that the earliest stars in the universe, the ones that were formed just out of the primordial hydrogen and helium left over from the Big Bang, they were capable of getting vastly larger, maybe hundreds of times the mass of the sun, maybe thousands, maybe tens of thousands, maybe millions. Like, we just don't know still. And it's believed that it comes down to the heavier elements that are in the star, the pollution, the metal pollution. And of course, astronomers think that anything heavier than helium is considered a metal. And so when they talk about metal pollution, they could very much be talking about oxygen, but still that metallicity of the star has some effect on halting its growth. But there's probably more to it as well. So, really the question is, you can't get a star without cold gas. You need to have large reserves of cold material. If the material is very hot, then the atoms are jiggling and they don't want to collapse down. You don't want to get a star. And so when you had some cloud of gas, it's able to cool down so that it's, almost no motion in the particles, then the gravity can pull it together. Usually you'll get some kind of event that gives it a kick, that begins this collapse. But it's possible that these largest objects are somehow interacting with their environment in a way that maybe the magnetic fields, as they're setting them up, are able to cool down the gas and maybe channel away the hot gas away from the star and funnel cold gas into where it's forming this material. So this is like a big question. Like, we still don't really know this. And there are, this is at the very limits of what the James Webb Space Telescope can perceive. Maybe if it sees a bunch of gravitationally lensed galaxies, it might be able to see examples of the first stars forming. More likely, it's going to be able to find the pollution that came from the first stars in galaxies. And it looks like this has already happened, that James Webb has been able to find galaxies that have the results of those first stars dying, and maybe you can work back forensically to figure out how those first stars formed. But this is still a big unsolved question in astronomy right now. And the answer to this question might help answer the other big question that astronomers have, which is, how did supermassive black holes get so massive so early in the universe? Like, we think that black holes came together one by, you have a star, dies, black hole, another star, dies, black hole. The two black holes come together, you get a more massive black hole, they find another black hole, they merge, and you work your way up from a stellar mass black hole to a supermassive black hole with millions or even billions of times the mass of the sun. But that's a lot of black holes finding their way to each other. Well, maybe if you get those first stars forming very quickly with tens of thousands of times the mass of the sun, then maybe you get black holes with tens of thousands of times the mass of the sun, and they merge together, and that you're able to climb that mass ladder more quickly. So figuring out how the first stars formed is still a really big challenge, a big mystery in astronomy, and would be one of the most exciting things that people could discover. Erica and Mars. I read an article about how dark matter doesn't exist and the universe is 24 billion years old. Did you see this article? I haven't, I've seen it. Yes. I looked at the paper and I was like, nah, I'm going to pass. Now, we did report on his previous research where he thinks that the universe is 24 billion years old, and now he's also including the dark matter doesn't exist part. And he's making a couple of assumptions, and one of them is that he's using this pretty much discarded theory called tired light, that that the universe is bigger than it looks because the redshift that we see of light is coming from light getting tired over time, that the photons aren't just getting redshifted because the universe is expanding. They're actually, as they travel over longer distances, they are changing, the reddening as this is happening. But there's a lot of hoops that you would have to jump through for this to be correct. So you see this all the time, that a scientist comes up with an out of the box idea, they present it, and then other scientists consider whether or not it meets their requirements for the amount of evidence that they see. And if it doesn't, or if that it's just not compellingly interesting as a scientific theory, then it doesn't go any farther. And the researcher is obviously motivated because he wants to come up with a new theory to help explain additional mysteries in astronomy. But it's a very high bar to clear, right? When you think about what a scientific theory has to do, it has to, you have to explain all the existing phenomena. And so this theory that this researcher is making has to explain everything we see in the universe, right? That the current theories that the universe is 13.8 billion years old address. And so the first thing you got to do is you got to match that. Then you've got to explain some mystery in the universe with a level of precision that meets the requirements of the scientific community. And then you've got to make some kind of testable hypothesis that people can go out and measure and confirm and show that what you're saying is right. You know, Einstein is a great example with relativity. You know, relativity matches Newtonian physics for explaining the motions of things in the universe, but it also took a mystery, like why is Mercury not exactly where it's supposed to be? And then it has made a series of additional testable predictions that still, 100 years later, physicists are still coming up with new ways to test the predictions that Einstein made. So this, if that is like the gold standard of how you do science, then the other side of it is you have a hypothesis, you present a bunch of math, you let people consider it, and then you never hear from it again. And that's where this probably is going to be on that, on that spectrum. Hey, Marcus. Can nanofibers slice a ship in pieces? Yeah, we're going to talk about the three-body problem in a second. After we go into overtime. John R. Wachowski. Would you go to Mars if asked to? I don't know if asked to. How would that work? Like someone would come up to me and go we need you to go to Mars. Get your ass to Mars. Okay, I guess if I'm I'm forced to go to Mars. Would I travel with a team of astronauts to go and explore Mars? Probably not, I think. I would let other people do that. It's kind of like if someone said, would you be willing to go on a hike to the top of Mount Everest? I hike. I do multi-day hikes. I do a lot of stuff in the outdoors, but that's a level of danger that I am not ready to put myself into. And Mars is the next level. I mean, you're going to commit several years. You're going to have to experience large amounts of radiation. You're going to increase your cancer risks. You're going to be away from your friends, your family for years. You're going to help humanity's exploration of Mars, which would be super cool. And you'd be on Mars. You'd experience low gravity. You would be being on this other world. You'd be living the sci-fi dream. But I think that would get old pretty quick. I think your first year, you'd be like, no. So your first day, you'd be like, whoa, this is amazing. I'm on Mars. And you're talking to the other astronauts I'm on Mars. I know, right? We're on Mars. And then the second day, you're like, oh, wow, it's Mars. But there's no water. There's no oceans. There's no trees. And you've got to be there for 18 months. And so near the end of it, you're going crazy. So I don't think I'm cut out for that. But I know the people are. And so like, why would I want that seat? I would let other people take that seat. Now, I would go to the moon if it was safe. Like if the moon was, people went to the moon all the time to go to the big amusement park on the moon. That's a Futurama reference. I would do that. That sounds great. But I'm not going to be one of the first people to go to the moon. Again, very dangerous. There are people who are willing to put themselves in that kind of danger, not me. So I think someone said I'd go to Mars after Elon Musk's grandma goes. I think that's a good, that's a good description of when to go. Is, when you're taking elderly people on cruises to Mars, it sounds like it's safe at that point. So, Josh Schultz, I covered the supernova right at the very beginning. So if you missed that. Austin Sapp, do we know of any moons that have moons orbiting them? Like moon squared situation. So what you're talking about is known as a moon. That is, that's not the scientific term, but I think that's sort of what we're moving towards as the generally accepted definition of a moon orbiting around a moon. And we don't know of any moons. And it's theoretically possible, but it would require like really careful setup for you to be able to get that, because every planet, every object gravitationally has this thing that's known as the Hill sphere. And this is its region of gravitational dominance. And then at a certain point, other objects can then capture them away from you. So the Earth has its Hill sphere. The moon is trapped in it. The moon is going around the Earth. But if you tried to put something in orbit, say geostationary orbit around the moon, it is outside the moon's Hill sphere. So anything that you put in orbit around the moon will just be captured by the Earth. And so anything that, so if you tried to give a moon to the moon, then eventually the Earth would try to capture that moon. There's like a few places in the solar system where it would theoretically work. Like if you took Neptune and you moved a moon out to exactly the right distance, and then you put a moon around that moon, then the whole thing could be stable and would last for the age of the solar system. But we haven't found any, and that's probably just because they're not stable. But I mean, when you think about the way the universe works, like gravity, it's all just cycles, right? You've got superclusters with galaxies orbiting around the supercluster, and stars are orbiting around inside the galaxy, and there are planets orbiting around the stars, and there are moons orbiting around the planets, and then there are satellites flown by aliens orbiting around those moons. So, it's fractal, man. All right. That's the end of the main show. Then we will switch over into overtime, and we will talk about the three-body problem. Tropical Tom Garcia, will the number of questions about the three-body problem one day exceed the number of questions about Lagrange points? Maybe. Yeah. People would love to. And like literally the actual three-body problem, not the TV show. Okay, so I have to do some administration stuff. I have to record a bunch of intros and outros, so it's going to take me a couple of minutes. And while you're waiting, you can go to the bathroom, grab yourself a snack. You don't have to watch this. It's okay. But come back, because we're going to do overtime. All right. What's the difference between a nova and a supernova? Why does the moon look upside down in the southern hemisphere? Is there any limit to the periodic table? Okay. What is the difference between a nova and a supernova? Why does the moon look upside down when you're in the southern hemisphere? And is there any limit to the periodic table of elements? All this and more in this week's question show. Welcome to the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather them up and I will answer them here. Before I get into this week's show, I just want to celebrate that this is the 25th anniversary of Universe Today. In other words, I have been a space journalist for 25 years. I founded the site on March 23rd, 1999, and here I am, 2024, still doing some version of the same job. So thank you everybody who has supported Universe Today over the years, both our patrons as well as everyone who has gone to the website, everyone who subscribes to the newsletter, watches this stuff on YouTube and so on, listens to the podcast. I really appreciate everybody's support and this incredible team of writers and video editors and programmers, audio editors that work with me to bring you all of this material. We love it. We've been doing it for 25 years. I've been doing it for 25 years. And we will only stop when the robots do a better job than we do. And I think that'll take a while. So here's 25 more, at least. All right, let's get into this week's question show. I hope you noticed the Star Trek planet name that appeared above my shoulder. This is a way for you to vote, to tell us what you thought was the best question of the week. And last week's vote was for Dark Star 420. Isn't there a star heading towards us from the Large Magellanic Cloud? And it sort of led into this really fun conversation about stars mixing between the Milky Way and Andromeda, and led to some news that was reporting. So thanks for everybody who voted. Now we're going to put up a different Star Trek planet name above my shoulder. I'm probably pointing at the wrong shoulder. Maybe it's the right one. And then you wait until the very end of the episode and then just write down in the comments the planet name that you thought was the best question. Then we'll gather it up and we will celebrate the vote next week. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. That's like 3 hours long. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Gary Hash, Martin, Bill Doster, Jamie D, Dougie Stewart, Phillies 2012, Stephen Krasaki, Mike Keats, Black Hole, Robert Revak, K220 Mark, Michael Costigan. Join the club at patreon.com/universetoday. All right, those are all the questions that we had this week. Thank everyone for your support, everyone who joined me live for the show. We do this every Monday at 5 p.m. Pacific. So if you want a twice as long episode and have conversations with other space fans as well as me, and we chat about it, there's the regular show and then there's the overtime. Come join the live show. There'll be a reminder somewhere here on the channel for the next event, but it will be a Monday at 5 p.m. Pacific, unless I'm watching the eclipse. All right. Anyway, there will be more live shows coming up in the coming weeks. Now, I'm going to talk about another smaller space YouTuber, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Antonio Lofilara, David Gildenine, Dougie Stewart, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Mark Anstis, Paul Rohrbach, Stephen Krasaki, Stephen Fowler Munley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other patrons. All your support means the universe to us. It's going to change the color. I don't know if you want a new color, chat. Here. All right. I have been directing you towards YouTubers who are doing a great job here on the platform, and yet for some weird, bizarre reason have less YouTube subscribers. They're sub 10,000. We have to fix that. So this week, I want you to check out Kyle McCaslin, who is an amateur astronomer, teaches you how to do astrophotography, but also talks about both the gear as well as how to view transits going across the sun, how you can see planets during the day with a telescope if you're very careful and you know where to look. So very cool channel. I really like that kind of practical, hands-on, I've got a telescope, here's what you can do type of material. Great astrophotography as well. So check out Kyle McCaslin's channel. And again, tell me if there are YouTubers that you like, people who are like great science communicators, but for some weird reason have less than 10,000 subscribers. Let me know so that we can promote them and get them more subscribers. All right, we'll see you next week. Oh, I didn't give you this, Chad. Okay. All right, I'm going to stop the recording and let's go to overtime. $254. Okay. Hello, patrons. This is the overtime audio for the question show that we recorded on Monday, March 25th, 2024, as part of question show 254. All right, enjoy the additional audio. All right, so the question I've got a bunch here is, did I watch the three-body problem and what do I think? So I'm going to try to give you a spoiler-free version of what I thought about this. And so just for context, I read the original three-body problem and all three books. So the Remembrances of Earth Past. And so I've read the original books in English. I haven't read the Chinese yet. I could, but I kind of don't care anymore. Weirdly, one of the reasons I wanted to learn Mandarin Chinese was to read these books in the original Chinese. And now that I probably could, I don't care. So I want to find other science fiction stories that I'm unfamiliar with. Anyway, so I read the books. I have watched the Chinese version of the Chinese adaptation of the first book, and it is long. It's like more than 30 episodes. It just follows point by point exactly the events in the book, which is kind of crazy that they would do this. I mean, just you see this with Korean dramas, with Chinese dramas, like it's bonkers how many episodes they make when they do a show. Like in the West, you'll get 8 episodes of your show. In China, you get 40. And, and maybe it should have been 8. So I saw that and it was pretty good. It was a stunningly sort of accurate retelling of the story, but there's a lot of problems with the story. And so they did what they could, but there's a lot that needed to be cut out. So we got the Netflix version of the three-body problem, and I really enjoyed it. I thought it was terrific. Like as a piece of science fiction storytelling, I thought it was well executed. It shortened dramatically stuff that just seemed to go on forever. Like there's a scene where Yao Wenjie shows up at the facility in China, and she goes from you're an astrophysicist, right? Okay, they bring her in to she's doing important work on the project with no in between. It's understood. She showed up, she provided useful service, and she was promoted to be able to work on more complicated activities. In the book and in the Chinese version, like it's episodes of her trying to figure out ways to get more responsibility and have interpersonal problems with other people on the team and so on. So I thought it was great. There are some really pivotal scenes that happen in the book, and they're covered really well in the show. You get, like I say, there's the army computer scene, which was done great with sort of good comedy. There's the boat scene, which is so. I don't want to spoil because like if you have no idea what's going on, and if you haven't watched the Three Body Problem and you haven't read the book, you know what the boat scene is, then it's kind of like watching Game of Thrones and watching a wedding and kind of go like, wait, what? So yeah, but in the Chinese version, they did a great job of that scene as well, but they kind of took away the horror of it by making a bunch of bad people in the boat. And in the Netflix version, it's extra horrible. So the first season of the Three Body Problem on Netflix, it's 8 episodes, but it not only covers the first book, but covers the first part of the second book as well, and sort of mashes all together into one story that's very coherent. And I thought that was a really smart move that they did to kind of bring those pieces together. They adapted it more to, like, obviously it's set in London now, as opposed to being set in China. Many of the characters are, English, but they did a good job of keeping the key characters be Chinese, who were really influential in sort of what makes the plot unfold. And I think the problem with the book is that it is like really a difficult read. It's very boring. The first book is boring. The second book is great, and the third book is mind-blowing. But a lot of people, when I say, oh, you should read this series, they read the first book, they're like, oh, this is dumb. I don't really enjoy it. I don't get it. I didn't like it. I totally agree with you. It's the second one and the third one where things start to clip and the ideas are crazy and it just gets weirder and weirder and more amazing. And so you kind of have to watch it. And then the other problem is that the themes discussed in the book are seen from the lens of a person who is okay with the authoritarian power of China and has defended Chinese authoritarianism many times in the past. And it's hard not to grapple with the ideas that are being presented in this, at the same time knowing that these all were fine by the censors in China. And so it's sort of like a troubling book to wrestle with when you think about the context of what it was written in. And I think having this Western adaptation of it hopefully will pull out all of the good story, the great concepts, the great ideas, without having to necessarily pay homage to the environment from which it was written. And I think that's all for the good. So there are, like, if you enjoyed the first one, it should be way better. It should just get better and better and better as the next 2 episodes. So I think the next 2 seasons, like I said, book 2, like the concept of this show, or the concept of the book, really is, like, normally when there's an alien invasion, it's this very acute issue that humanity needs to defend itself immediately. They need to drop what they're doing. They need to defend the planet against these alien invaders. But the Three Body Problem sets this problem out 400 years, that this is a generational issue, that these spacecraft, the aliens are coming, it's going to take them 400 years to get to us, and that this problem will not be handled by our children, our children's children, generations down the line. It is a problem for the future. And this is a metaphor. This is of what we do as human beings. We don't think about the future implications of the decisions that we make today. We not only should we consider what impact we're doing to the environment, to humanity, to politics, all this kind of stuff, not what impact does it have today, but also what impact is this going to have on our children, on future generations. It plays very little in our thinking. And so how does a society react to Armageddon that is going to take 400 years? That you panic for a while And then you have to live your regular life. You have to go to work. You have to drink your coffee. You have to have a job. You got to commute. You're going to have children or decide not to have children. Life goes on with this shadow that is forming, casting this long shadow across humanity's future. And it's such an epic concept to wrestle with. And I don't think that, Cixin Liu did the best job in wrestling with it. He sort of went the path of smart people are going to come up with clever plans and they're going to have absolute authority and people are just going to follow and do whatever they say and things are going to end up how they end up. And I don't think that was the right lessons to learn. Like it could have been, or, just in general, to have this, what's the term? Like a terminal diagnosis for your civilization, but it is far in the future, is a really compelling concept to wrestle with as a science fiction story. And so I'm looking forward to them exploring it. So this was a good show. I think it's worth watching. There you go. That is my take on the three-body problem. All right, back to the questions. K-Swiss, when Betelgeuse turns into a black hole or vice versa, what impacts should we be prepared for in our solar system? No impacts. We will see a bright star in the sky for a few months and it will fade away and then Betelgeuse will be gone. So that's the impact, was that Orion will be missing its shoulder pad. Alaska B, any updates on a submarine probe to Titan? I want to see methane whales in Krakamari. There are no updates. There was a story we're working on at Universe Today, probably the next couple of days. One of the writers claimed it, that the European Space Agency just announced their priority to send a probe to Enceladus. And this was after they had considered a probe to Europa and considered a probe to Titan. So they considered Titan and Europa, and they chose Enceladus over that. So there's less of a chance of a submarine mission going to Titan. And I agree with you. Boy, it should be great. Mr. Mark Meadowland, what is the first megastructure humanity will construct? I mean, this idea of a megastructure, like a Dyson sphere or so on, I don't think that we get megastructures built intentionally. I think they just happen over time when you look back and you go, hey, we just made a megastructure. We just completed a megastructure. I mean, think about cities. Think about megalopolis, like the entire eastern seaboard of the United States, where you've got almost continuous cities from New York, north of New York, all the way down the coast. It just goes on and on and on, city after city after city. It is a megastructure on the scale that our ancestors never could have imagined. And yet there's no point someone go like, I'm going to build a giant city that's going to go on for hundreds of kilometers. People build houses, and after a while, the cities all start to come together. So that's like a megastructure. And so even like a Dyson swarm, we have already begun building our Dyson swarm in that we have launched spacecraft into space that are harvesting solar energy and they're putting it to work. Yeah, it's a tiny fraction of the illumination that's coming from the sun, but that's how it starts. Next year, we're going to launch more. The year after that, we're going to launch even more. And eventually, we will be launching some percentage of the sun's total output in solar collecting arrays that are taking the energy from the sun and they're doing some functional purpose with it. And eventually, we will look back and go, hey, check it out. We're using up all of the energy coming from the sun. How cool is that? Anyway, what's next? So I think with mega structures, you don't just simply begin building them. They have to be useful at all levels. Sorry, just looking for another question. Edward Fox, why is the corona of the sun hotter than the surface of the sun? So this is one of the mysteries in solar astronomy. And so one of the big questions that scientists are wanting to answer is, why is the corona at millions of degrees when the surface of the sun is only 5,800 degrees? What is the difference? What is this coming from? And it's not a 100% closed case at this point, but it appears to be that you've got this magnetic connection reconnection that's coming from the surface of the sun that is accelerating particles off of the sun. They're interacting with particles higher up in the atmosphere, and they're heating up the corona around the sun. That there are these like tiny flares across the surface of the sun that are going off all the time and heating things up. But the Parker Solar Probe, the Solar Observer, the new Daniel K. Inouye Solar Telescope, one of the jobs of all of these new instruments is to really understand the mechanism of what causes the coronal heating. So the jury isn't quite out yet on what's going on that causes the corona to be so much hotter than the surface. Kevin, do photons experience time while traveling? If not, are they essentially skipping forward in time instantaneously from their perspective? I mean, this comes up quite a bit. Like photons are not known for their opinions. So, do you really ask a photon if it's experiencing time? What does it mean to be a photon, man? But according to, like, if you put in the amount of like relativity, if you look at relativity and you want to calculate the amount of time that a photon experiences when it's traveling at the speed of light, the answer is 0. That a photon, from a photon's perspective, it is emitted and it is absorbed by whatever hits at the same time, simultaneously, and experiences no time in the journey. And so if we could travel at the speed of light, we would experience the same thing. If we could travel faster than the speed of light, we would experience negative time. Figure that out. Samurai Hash. I can't recall hearing much from the Parker Solar Probe. Any idea what it's up to lately? So we just published a story on Universe today about a paper that I found. Parker Solar Probe has experienced dozens of coronal mass ejections in 4 years. Like, it's gotten hit, flown through, I think, 40 coronal mass ejections in 4 years. Maybe it's 18. 18 coronal mass ejections? I think that's the number. Anyway, so we've got a story on Universe Today all about it. I should get someone from the Parker Solar Probe to interview, though. That would be really cool. All right, mental note. Visto Tutti, if a CMB photon never hits anything, did the universe really happen? If you shine your flashlight into space and some of the photons coming from your flashlight never interact with anything and are never observed, did you really turn your flashlight on? Yes, you did. Avel third, is a black hole really a hole, or is it just a solid mass that just attracts everything in its vicinity towards it? A black hole is just an object with mass like a star or the Earth or you, and it just distorts space-time in the same way that all of them do. And so anything that's traveling in a straight line as it passes near a black hole gets its path distorted by the amount of mass and its distance to the black hole. So it's not attracting things. It's causing this dent in space-time. If you replace the sun with a black hole of the exact same mass, all of the planets would still just orbit around it exactly as they had before. There's nothing special about a black hole as it relates to the interaction of its mass on the universe. B. Guzman, Europa, when are we going? 2025. And also the Europa juice, the European juice mission has already gone. It is on its way to Europa right now. But the Europa Clipper launches next year. Roquaf. Fraser, are you still obsessed with what you were obsessed with last week? No, my obsessions change hourly. What am I obsessed with right now? I don't know what I'm obsessed with right now. But I'm often, like, what I'm obsessed with gets messed up when I do the question show, because now I'm thinking about the Parker Solar Probe. I'm thinking about how I want to find out more about what it experienced with those coronal mass ejections. So I guess there's, like, it's a bad time to ask me what I'm obsessed with. Gene Hansen, I'm playing Subnautica right now. What are your thoughts on intelligent life evolving on a pure water world? This has been discussed in the scientific literature. Like, what if a civilization evolves, if intelligent civilization evolves on a water world? You can imagine, like, we're pretty close with whales and dolphins, octopuses, that maybe one of them gets to the point of intelligence. And it would be kind of depressing, because they wouldn't be able to light fires on underwater. And it seems like fires are a really important key to being able to move forward in your technology. You need, like, what fire lets you do is it allows you to take chemical energy that has been stored up in the bodies of plants and release it instantaneously, effectively, for energy use that you can then have mechanization. You can have machines, you can use transportation, so on. And so the intelligent dolphins, even if they had hands, wouldn't be able to light fires in a world of water. And, like, hopefully they'll have a seafloor that they can interact with. And you can imagine some really clever dolphins building some kind of platform at the top where they can start to do experiments in their, I don't know, exosuits. I mean, I don't know how they'd be able to sort of leverage themselves up. So it would be really tricky to have an advanced civilization evolve from a water world. It just, like, probably wouldn't even occur to them. But if they're intelligent, then you kind of don't bet against intelligence. Like, if we took all of humanity and we had to live in the ocean, like, we knew that that solid ground was going to be taken away from us in 400 years by the Trisolarans, would we still be alive? And I think we would figure something out. So who knows? Maybe some intelligent civilization that lives in the water would figure something out. They'd harness chemical energy in some way. They would adapt living creatures. They would, genetically adapt creatures to be able to do the kinds of things that they need. So who knows? Sounds like a science fiction book. Jimmy the Chicken, how do we know that the tired light hypothesis is invalid? So it has made, and I haven't looked at it recently, but the gist is that if you see light moving, like, we see light that's coming from the cosmic microwave background radiation. And so we see it having been red shifted over the billions of years that it's taken to reach us. But we can see things that are emitting light sideways. And so if light was getting sleepy over long periods, over long distances, that would change what we see in the large scale structures of the universe, because we'd be seeing light going sideways, being emitted by galaxy clusters and interacting with their environments. And we would see that red shifting in a way that doesn't come from the expansion of the universe. That's the gist of it. I haven't done a debunking of it recently. But essentially, when astronomers discovered that the light coming from distant galaxies was redshifted, and then they realized, thanks to Hubble and others, they realized that the distance to these galaxies, the farther away they are, the faster they're moving away from us, sort of was one explanation. And then the other explanation was, no, we're not seeing things moving away from us because of redshift. We're seeing just because the light is losing energy over time. And so then, and so that makes predictions that then astronomers are able to check. And you have, if light does tire, then you should see this kind of observations in the universe, and we don't see that. But if light is being redshifted by the expansion of the universe, we should see these things, and we do see them. And so over time, the scientific consensus is that the redshift, cosmological redshift, is the correct answer, and tired light is the wrong answer. But that's my synopsis of what I've seen. Hello from Alberta, from John Gix. If the sun is replaced with a black hole of the same mass and same brightness, will there be a difference for us? So, black holes aren't bright. Black holes absorb all the radiation that comes from them and give off pretty much no illumination. So the only time that you can get a black hole that's actually giving off illumination is if it's consuming material. Then material piles up in the accretion disk around the black hole, and then you get light coming from that accretion disk as all the material that's waiting to die. And it is, the brightness of it depends on how much material is being piled up. And the majority of that radiation is released in the higher energies, X-rays, gamma rays, and it doesn't follow the same black body release of energy as a star does. And so to be close enough that you're getting the same kind of illumination from the accretion disk around a black hole, you're probably getting a lethal dose of radiation from the X-rays and the gamma rays. Pelican 666, is actual film better than digital for astrophotography? I don't think so. I'm sure there's people who are purists that really love film compared to digital for astrophotography, but film is so, you expose camera to the sky, and then you don't know if it was a long enough exposure, whether it was overexposed. When you think about when you're using digital and you're taking exposures, and then you're double checking to see if it was good enough, and then you're figuring out how long to do this. You take hundreds of images, thousands, and then you stack them up on computer. No, digital has been a revolution in astrophotography. And think about the Hubble Space Telescope. It's digital. They don't have film cameras on board the telescope. So, from an image quality standpoint, no. And from a practicality standpoint, absolutely not. In fact, a lot of the technology that's used in digital cameras and the sensors used for, in your phone, that technology was developed as part of things like the Hubble Space Telescope. Kirk Thompson, any news on Trojan missions? Well, the Trojan mission is Lucy, and so Lucy passed its first asteroid, Dinkinish, which I think had a moon as well, and now it's on its way out to one of Jupiter's Trojan regions, and then it's going to fall back down, go around the Earth, and go back to the other of Jupiter's Trojan regions. So no news until Lucy gets to Jupiter's Trojans. Let's see what the Lucy mission milestones. What's it? I think it's 2029. Let's see the timeline. 2027 is when it reaches the first Trojan asteroid. So it already encountered Dinkanish, and then in 2025 it's going to encounter Donald Johansen, asteroid Donald Johansen, and then the first Trojan is Eurybates in 2027. So that's not long, 3 years. That's really cool. Wow. Thank you for asking the question. Let's see. Man, so many questions today. Rafia Parveen, how do black holes create plasma jets? So I mentioned before, you get a black hole, it's rotating, materials falling into the black hole, wants to be consumed by the black hole. Black hole just can't eat all the food that's arrayed in front of it. It starts to choke on it. And so what you get is you get this accretion disk of material that starts to build up around the black hole. And the example that you see is, like, think about when you pull the cork on your bathtub and you get water swirling around inside the bathtub. That's the water waiting for its turn to go down the drain. Although a black hole is in a hole, it's just a sphere, but material's falling onto it. But anyway, you then get as the black hole is turning, you get these large magnetic fields that are interacting with this material that is in the accretion disk, and you get then these jets form, and it siphons material out of the accretion disk and up the jets above and below the black hole. Chaomatic. Is it possible for a star like our sun to be the size of the Earth or the moon and still keep the same properties as the sun currently has? No. The sun, like the size of the sun, depends on the amount of mass in the sun, the amount of just raw hydrogen and helium and other material that is in the star. That is the amount of total mass. Like however much mass it began with, that's what it's got. But then the size of the sun is dependent on the temperature. So at the core of the sun, you've got hydrogen being fused into helium, and this is releasing energy. And this is like an outward radiation pressure that is pushing out away from the sun. And then to balance that, you've got the material of the sun that is being pulled inward by its gravity. And then you get this balance, the outward force from the radiation pressure, the inward pull from the gravity, and you get the sun. But later on in the sun's life, it's going to switch over to burning hydrogen into burning helium into heavier elements. And this will increase the temperature at the core of the sun. And this will actually cause it to puff out into a much larger version of the sun. This is that red giant that's going to gobble up the inner planets. And then later on, the sun will have blasted out its outer layers and the core will cool down, will shut off, no longer be doing fusion, and then it will shrink down to be the size of the Earth. But it won't be like the sun. It will still be putting off a lot of illumination. It will be a white dwarf. It will be a dead star, but it won't be putting out the same amount of illumination as the sun. So no, the size of the sun, the temperature of the sun helps define the amount of radiation that's coming out of it. Stephen Collins, what was the last space news that made you obsessed? All right, I don't know. Let me check and see what we're currently... Actually, you know what I'm going to do? I'm going to go to the list of stories that I haven't prepared for the writers yet. So these are stories that I thought were really cool, but I haven't assigned them yet. So I'll just give you an idea of the kinds of things that I think are really cool. the one here? So mass supply from Io to Jupiter's magnetosphere. So how much material is going out of Io and is accounting for the charged particles that are in Jupiter's magnetosphere? I don't know. The enrichment of extragalactic first stars in Large Magellanic Cloud. That's kind of cool. And then I've got a whole bunch of stories from the Lunar and Planetary Science Conference that happened a couple of weeks ago, and we're digesting them a couple a week. But which caves on Mars are safer to live in? Venus is an anchor point for planetary habitability, pushing the limits of in situ organic detection, determination of lava tube depth and shape from topography, bacterial tolerance to high physical pressure relevant to Europa and the ocean worlds, identifying landslides in the Alta Regio on Venus, landslides on Venus. How early could the giant impact have taken place? So what's the earliest possible impact that formed the moon? The prospect of detecting volcanic signatures on an exo-Earth using direct imaging. So could we see volcanoes on an exoplanet using direct imaging with, say, the Extremely Large Telescope or the Habitable Worlds Observatory? The importance of Martian atmosphere sample return. So imagine you fly a spacecraft to Mars and all it does is dips through the atmosphere of the Martian atmosphere, collects a bunch of samples, comes back to Earth and delivers them like we saw with OSIRIS-REx. That would be cool. Detection of airbursts on Titan with dragonfly pressure and seismic instruments. So are there meteorites crashing into Titan? And it has a very thick atmosphere. And could the Dragonfly mission, which is going to be this nuclear-powered helicopter flying around on Titan, would it be able to detect these impacts happening because of the seismic waves or just the changes in pressure on the atmosphere? Cool idea. So that's the kinds of stuff that I get. They all get put into my short list, and then I process these stories for sending out to the writers. Jake Snyder, why is the top of Saturn shaped like a hexagon? So it probably has something to do with fluid dynamics. There was a science museum in Vancouver called Science World. Any people from Vancouver know what I'm talking about. And they've got this big rotating, they have one of the Exploratorium in San Francisco as well. It's this big rotating table with a fluid inside of it with different particles. And as you spin it, you get these weird standing structures start to appear in this fluid. And this is one of them. There's some kind of fluid dynamics happening in Saturn that is causing, in the cloud tops, that you're getting the hexagon forming. And you can do experiments that mimic it. Orlando Erickson, is there an Oort cloud around other suns? Almost certainly. We've never seen our Oort cloud, so we definitely haven't seen Oort clouds around other stars. But I mean, there are just so many comets coming from the Oort cloud. You'd have to assume that it's a common feature in other solar systems. Dougal, if you had more free time, what would you be doing? I'm pretty good with my free time. People are like, I don't understand how you work so much with all of the interviews you do and all the podcasts you put out and all the writing that you do and all the work you do with the Universe Today team and so on. Well, it's a team. It's a job. It's actually a reasonable... I don't work super hard. And I have a ton of leisure activities that I do. The main one right now is I'm doing rewilding, where I am cutting out invasive species and thinning out the Douglas fir monoculture on our property and replacing it with more diversity of plants and trees. And I'm running a wood chipper and cutting down trees like a Canadian lumberjack. And then we're bringing in, hopefully, we're seeing more and more species return to the property now that we've got all of these spaces opened up in the canopy. Because overgrown forests are like deserts. that you're going to have life up at the very top, but down below it's stark and feels very scary, actually, when you walk through a forest where the canopy, like when people have planted trees and they've never thinned it, it's just really, it's quiet and there's no birds and there's no wildlife and there's no underbrush, just trees packed together casting a shadow. I know it's a total rabbit hole, but anyway, that is, and it is bottomless. Like we've got 80 acres that I'm trying to restore, and I only have so many hours in the day, and I have other gardening that I like to do. So that is my, and then apart from that, I mean, we travel a lot. Well, we did before COVID, but I'm about to travel. I'm about to go see the eclipse, and then I'm going back to Japan. I know you were all remembering when I was supposed to go to Japan with my son, and then we got COVIDed. Well, now we're going back to Japan in May. So hopefully I'll be able to shoot some videos while I'm in Japan. And then I've got a trip that I'm taking to Spain in June, and then probably going to Italy. So, and then we're going to try and figure out, like last year we wintered in Tucson, Arizona for a month just to figure out what it was like to not be in Canada in the wintertime. And it was nice. So we're trying to figure out some other place to go. Maybe Portugal, maybe Thailand for a couple of months this time around. So we're going to see if that works. So travel, hiking, mountain biking, video games, reading, hanging out with my friends, and cutting down trees is what I would do if I had more free time. But I feel like I have plenty of free time. The thing that I do is I don't look at my phone. So, like I see everyone around me looking at their phones all the time, and it's a thing that I don't do. I have deleted all of the useful, interesting stuff off my phone. My phone has my email on it, but that's boring. My phone has my YouTube comments, which is great. I love to read the YouTube comments, but apart from once I'm up to date, there's not much more time to be spent. But my phone has nothing interesting on it at all. No social media, no news, nothing. It is boring. And that's huge. I think a lot of people lose a lot of time in their lives by spending time looking at their phones. That step one is wean yourself off of that process, because you like, if your mind is bored for just a second, you pull out your phone and you go like, I wonder what's happening on the news, and then you're just like, hours of your day disappear into that. And so once I removed that, I have tons of time. It's amazing. So yeah, I highly recommend that. So I feel good. I feel good about the how I spend my free time, and that I have plenty of it. T-Home, what is a good place to see the solar eclipse in Vermont or New Hampshire? I mean, who knows? I don't know. It all depends on what the weather's like. I think big picture, you've got to decide, are you going to chase a place that's sunny? Are you going to try to go, like, that's probably Mexico or the southern US, South Texas, things like that. If you're going to stay close to home, then you know what your weather's like in early April. Here, it's not great. So if I had an eclipse coming through British Columbia in April, I wouldn't count on my chances of actually seeing the sun dim, or like being able to see it. Like everything would get dark, but I wouldn't actually see the eclipse itself. So that's why we're going to Texas. I could go to Canada. It's going to be passing through Canada, but I wouldn't try to see an eclipse in Canada in April. I would go to Texas. So apart from that, like that's the top priority, is to get good weather, and you have to stay mobile. That on the day of the eclipse, you need to check and see what your weather forecast is and find out around you where on the eclipse path is there likely to be clear weather, and you got to be ready to travel potentially hundreds of kilometers to get to a place with clear skies. So that's all that really matters. So you know what your weather's like in Vermont or New Hampshire in April. I don't. time is it now? Okay, 10 more minutes. Don Archangel, with all the new AI robots being created, should we send those to do our exploration of the solar system? I mean, don't we already send our robots to do the exploration of the solar system? And there are artificial intelligence components on those spacecraft already. Like the Perseverance rover, when it landed at Mars, it picked its landing spot. It knew roughly where it was going to land, but it looked at images of the surface of Mars, evaluated them for any hazards, and then picked exactly the place that it thought was the safest spot to land. And there's no way that humans could have been able to handle that. The robot had to be able to do it. And I think we're in this, like we saw the Odysseus lander crack and fall over. We saw the Japanese Slim lander upside down. And if there was a human on board, like imagine if there was a human on board the Odysseus lander and was piloting it to the surface, lost the laser rangefinder, no problem. They could manually navigate by eye as they get closer and closer to the surface of the moon, which was difficult for a computer. But you can imagine some future where you've got really intelligent artificial intelligence programs, machine learning algorithms that are designed to do high-level autonomy projects in space, navigate, land on the surface of objects, manage their power systems, handle communications, and do science. Route finding, where they'd have to go across some jumbled terrain of boulders. You don't want to take time to go around this boulder, then go around that one. No, you just have the robot figure it out. And that kind of technology, that kind of intelligence is being built for future robots. So I love the idea that you build a large language model, an embodied robot that has been trained on 1 million hours of driving on Martian terrain and getting itself into every possible, bumping into a rock, getting caught in a sand pit, chased by Martians, and it's able to deal with all of these. And so they can be more autonomous. Then they can just give you the science. You can give them the high-level tasks. Go explore. Tell us what you find. And then it checks back in every now and then with the things that it's found. That would be awesome. Mickey Finn, has there been anything published from the OSIRIS-REx mission? So there has been a ton of stuff published from OSIRIS-REx, but it's all in that Lunar and Planetary Science Conference. There was like 2 whole days where scientists were presenting stuff on what happened with Bennu. And I've put a couple of those stories into the queue for the writers, but we haven't gotten around to it yet. But it hasn't gone through the traditional university, releases a press release, journalists pick it up and report on it. And that's why, I'm really happy with the kind of coverage that we do at Universe Today. We have people who, we find these stories early and we report on them. But there hasn't been a lot of like really big announcements made from OSIRIS-REx yet. The one interesting tentative science that we heard was that some of the particles formed in the presence of water. And so it might be that whatever Bennu was, it was a chunk of a world that had water present, which is interesting. I don't even know what that is. So Pelican 666. Does NASA pay attention to this broadcast or to Universe Today? I don't think they pay attention to this specific broadcast, but they absolutely, I have plenty of people from NASA who read Universe Today. And it's great because now when I reach out to people to do an interview, like, hi, my name is Fraser Cain. I'm the publisher of Universe Today. I saw your story, blah, blah, blah. Is there any of you interested in an interview? And they're like, oh, Fraser, I know what Universe Today is. That's great. I'd love to do an interview with you. And that's great, right? Because the reputation that I have allows me to interview people who would normally not have the time for it. And I have a relationship with all of the press officers at the different groups at NASA. So people at JPL and Goddard and Kennedy Space Center and so on. And so generally they like to be present when I do an interview with someone. So you don't see them, but whenever I'm interviewing somebody from NASA, there's often a press officer that is in the meeting with us, just listening. And I guess they will jump in if there's some, I don't know, if they feel like the interview is going off the rails, and it has never happened. And I think at this point now they don't even bother. Like they go, oh, it's Fraser. Okay, yeah, no problem. It should be fine. Because I'm not trying to do any kind of gotcha journalism, right? So, but yeah, I think our work is known at NASA and ESA but as human beings who are interested in space. And I mean, we've been doing this so long that I have people like, oh yeah, I used to listen to Astronomy Cast when I was in university getting my astronomy degree. And then I got my master's degree. And then I got my PhD. And now I'm working on this mission. I'm like, whoa, that's amazing. So you do something long enough and you actually start to have this impact on people's careers, which is really cool. All right. One more question. Starshine, what's for dinner? Any ChatGPT G astro food lately? Gastro food. Oh, I get it. Okay. Man, so what is the thing that we made? So my son is starting to get into meal planning, and so I had ChatGPT come up with a bunch of meal planning ideas for him, things that he could make in bulk and then put in the fridge or freezer to eat over the course of the week. And so then I sent him like 25 ideas produced by ChatGPT, chili and like new Thai peanut noodles and a bunch of other stuff. And ChatGPT always recommends stuffed peppers. I don't know why. Even when I tell it I don't want stuffed peppers, it wants to recommend peppers. So the thing that we made that was really good was this Thai peanut noodle dish. It was like and he'd never eaten anything like that. And so he was sort of like, I don't know, I'm kind of skeptical. And he's like, oh, this is really good. So I still use ChatGPT all the time. I hope you all do. I love doing experiments where I just give constraints. I'm like, I've got some cabbage that needs to be used up, and I've got some M&Ms. What do you got? Right? And ChatGPT works best when you give it constraints, when you really try to focus it in on and not let it just recommend whatever it wants, because it's always going to give you stuffed peppers. Instead, you say, I want a Ethiopian inspired meal that uses wild rice as the main ingredient. And then suddenly it feels like you've got something intelligent that you're working with to help recommend meals to you. All right, I think we're going to wrap up now. So thank you everybody for hanging out today for this week's question show. Thanks to John Seffel and Zapfan for being so helpful for organizing the questions and putting them in the database. I couldn't do this without you. So thanks to those guys. Thanks in advance to Chad and Anton. You're going to have to deal with this nonsense and edit it down. Yeah. And we will see all of you next week. Thanks, everyone.